Ladies and gentlemen, good afternoon. We have about 80 perhaps students here representing 20-some high schools locally. So we not just have business leaders and professional leaders, we have a lot of students, and we purposely put them in front. So all the ones on this side are basically students, except a professor from Washington University, a medical doctor who in a medical school who teaches there, my friend who's originally from Iran. But anyway, we're delighted that all of you can join. This is an event of the Asia Society jointly with Hang Lung. As many of you know, I'm the chair of the Asia Society Hong Kong, but I'm only the honorary chairman of Hang Lung. I'm the chairman of Asia Society Hong Kong, and then I'm the honorary chair of Hang Lung, and that's why I'm standing here. I'm delighted that representing Hang Lung today is the chairman Adriel, our CEO Weber Low, and our CFO Kenneth Chiu, as well as many who are on the board of Asia Society Hong Kong Center that are represented here. Welcome to all of you. We're delighted to have this program. Just a little history for everybody. 20-some years ago, Professor Shing Yao, who is a Fields Medalist in mathematics, Fields Medal is in mathematics, came to me with an idea. And the idea is to found a competition in Hong Kong, unlike most of the math competitions. Most of the math competitions have defined questions and defined answers. This is a competition which has no defined question nor a defined answer. It is research. We want to expose young people in Hong Kong. We have a lot of talents hidden somewhere in various high schools in Hong Kong that we want them to be exposed to high-level research. So any school in Hong Kong can apply, and they can send a team, and they have to present a proposal. We work for the first many years with Chinese University and more recently with Hong Kong UST, the president of which, Professor Nancy Yip, is here with us. But we still work with everybody in Hong Kong. We still work with Chinese U very closely. We work with Baptist U and Poly U and everybody basically in Hong Kong. The idea is to have these students come up with a research idea. We don't care how they get it, just come up with a research idea, write it up, present it, and if it is, we have professors from Hong Kong UST, Chinese U, Hong Kong U, and so forth, screen them, and if you make the cut, you'll be invited to participate to do a research, usually in the summer. And then in the fall, there will be a screening that is done by world experts, many of whom from Hong Kong as well as overseas, that would decide which 16 or so teams can make it to the final. And then those 16 teams would have to work very hard to come up with a research paper. And then there will be like a dissertation-like defense. And it's usually held at Hang Lung. And the students, either individually or as a team, would have to face some of the world's best mathematicians. We have a number of Fields Medalists, we have a number of Nobel laureates, and many other equally distinguished professors from around the world, grilling them on their research. And then every other year we do this, and then we decide to have who's a gold, who's a silver, who's a bronze, as well as some honorary mention. Hang Lung, let me assure you, is not part of the adjudicated. We don't qualify, we don't touch it. It's totally up to the professors led by Hong Kong UST now, together with their colleagues from around the world. And we are very happy to say that after 20-some years, we have been extraordinarily successful. I see the Croucher Foundation represented here. 6 of our winners have become Croucher Fellows over the years, and that really tells you how distinguished our winners have become. And other adjudicating panels that some of you may know is like Sir James Malise, Nobel laureate, 1996 in economics, who was at that time the master of the Morningside College at the Chinese U, his successor of which, Professor Nick Rollins, is here with us. He was involved in it quite much. George Smoot, who is also a Nobel laureate in physics, Richard Chen, the Wolf Prize winner in mathematics, Mok Ai Ming, our own Hong Kong U professor, Future Science Prize in mathematics, as well as many others. So this is really, I think, a wonderful, wonderful program to spark the passion for mathematics and for research among our Hong Kong's youth. Many of them have gone on to get PhDs, others have chosen other careers, and one of the most respectable I know of is to go back to their high school and become math teachers. And I'm happy to say that I think he may be here. Our 2014 silver medalist in the year 2023 led a team from Puijing, where he's now teaching, and received honorary mention. And we have, I think, two represented here today who were winners of the prize and become high school teachers. Can I invite all the ones involved in this program, whether you are adjudicating panel, the steering committee, I see quite a number of you here, as well as the winners. But let's first have the winners. The former winners, can you stand up? Where are you? I don't know if any of them have arrived. There's one. Oh, Owen. Hey, come on, Owen, stand up. Right. There's another one. 1, 2, 3, 4. Very good. Then can I invite all the professors who are involved in this effort to stand up, Master, and everybody else. That fellow was my student at Hong Kong UST 20-some years ago, and he's now an assistant professor at Hong Kong UST teaching mathematics. Anyway, so we are delighted that we have this program set up, but we felt that we should do more, not just twice a year, once every other year. So we decided to, over the entire school year, in fact, over the entire year, have all kinds of programs for the students. Many of the former winners, former participants have come back to mentor younger students to help them with the project definition and so forth, and it has been really a very, very satisfying experience. And then this being the how many years, Susan? 20th year? We decided, 20th year, right? So we decided to do a series of public programs, thanks to the publicly minded Hang Lung Property Company, so that everybody can come free and listen to some of the best world leaders. The first program was held in January this year. My brother, Dr. Gerald Chan, was a moderator, and two speakers are Professor Nancy Yip, the president of Hong Kong UST, and Professor Zhang Qiang, the president of Hong Kong U, on what is good research. And then 6 months later, in June, we did another program with several leaders in AI. It was a program on AI. We had a world leader, Harry Shum, Professor Harry Shum, who is the council chair of Hong Kong UST, formerly executive vice president of Microsoft. We have a French gentleman by the name of Antoine Blondeau, who is one of the most effective investors in IT, in AI in the world, together with Chinese U professor Helen Meng. They had a wonderful discussion right here on AI. This is usually followed by a private dinner. If you want to join those private dinner for for a more detailed discussion, that is usually the speaker, the moderator, and then myself, when I ask dumb questions to elicit smart answers. So if you want to join those, sign up as a member of the Asia Society, and maybe we'll invite you next time. With that, I will invite onto the stage today my good friends, Dr. David Ho, Dr. Dennis Low, as well as Dr. Stephanie Ma. I don't think David Ho needs any introduction. Suffice to say that in 1996, he became the Time Magazine Man of the Year because he figured out a way to make AIDS, turn it from a fatal infection to a manageable disease. And so that is really under the leadership of Professor David Ho at that time at Rockefeller University, and then the whole team recently migrated to Columbia, where he is now. Dennis Lo needs no introduction in Hong Kong, just like David Ho. Dennis is one of our own, meaning that he's born and raised. Oh, by the way, David is getting better now because David married a Hong Kong girl. Tara, wonderful to have you. And in fact, last night we had a celebratory dinner hosted by David and Tara, although they've been together as a couple for 20 years. It was only last night that they hosted us. David, I've been waiting for the dinner for a long time. Thank you very much. Anyway, Dennis, we all know that he has changed the life of many people, especially women. The prenatal test that is non-invasive is really now everybody in the world knows about it and uses it, and also to be used for detecting of cancer. And so Dennis is really one of the, just like David, the two of them have done so much good to mankind, I cannot begin to describe it. And I understand that the two of you have never shared a podium together, although you know each other. So, ladies and gentlemen, today is the first time that you have, ladies and gentlemen, David Ho and Dennis Lo together. Shall we give them a round of applause? Just to get on this stage to moderate is a serious event, and my staff have done a very good job. We interview a number of them, and last time we had Helen Meng. It turned out to be so effective. And today, ladies and gentlemen, not to disappoint anyone, we have another one, wonderful younger professors from Hong Kong University, Professor Stephanie Ma. Welcome. Okay, ladies and gentlemen, with that, let me invite the three of them to come up and turn over the podium to Stephanie Ma. Stephanie, take it away.
Testing. All right, Ronnie, thank you very much for the very kind introduction. And very good afternoon, ladies and gentlemen, friends and students. After what Ronnie said, I'm shaking, really. But it's really a pleasure for me and a great opportunity to serve as a moderator of this event and also to share the stage with really two icons in the science field that I so look up towards. Not just doing so well in the lab, but also translating their research findings into real-life applications that's most useful and most beneficial to human mankind. So again, what Ronnie said is that both Professor Ho and Professor Lo does not really need any introduction. But for the completeness of this panel discussion, I'm just going to do a very brief introduction of where they are now, what they're so renowned for. But most importantly, I want to share a fun fact, one or two about them that you may not know about. And I was actually quite surprised to learn. So Professor David Ho is, of course, the scientific director of the Aaron Diamond AIDS Research Center and the Clyde and Helen Wu Professor of Medicine, as well as Professor of Microbiology and Immunology at Columbia University Medical Center. He has really been at the forefront of AIDS research for over 4 decades, contributing to the understanding of HIV replication, which resulted in the development of a combination of antiretroviral therapy that transformed HIV from a previously fatal infection to a now manageable disease. So as a fun fact, Professor Ho shared that he's actually very sporty. He actually plays sports and has transitioned from basketball to tennis and now more recently to golf. He says it's a sign of aging. I don't think so. And in college, he also shared that he used to count cards while playing blackjack in Las Vegas. Oh, interesting, huh? So I'll be absolutely honest with you. I actually had to Google what counting cards meant. and maybe for some of you who like me do not know, counting cards is basically a strategy where you try to count the odds if you have the better bet or the dealer has the better odds of winning by counting the cards that were dealt. And so I'm curious to know, did you win big with the strategy?
He got kicked out of the casino.
So, okay. And so moving on to, of course, Professor Dennis Lo. Professor Dennis Lo is currently the Li Ka-shing Professor of Medicine at the Chinese University of Hong Kong and also currently the president of the Hong Kong Academy of Sciences. Of course, he's leading the research field in biology and diagnostic applications of cell-free nucleic acids in plasma. So, like Ronnie said, he's discovered the presence of cell-free fetal DNA in maternal blood plasma and has since then been pioneering non-invasive prenatal diagnosis using this technology, which has been so widely adopted and really shifted the entire paradigm of prenatal medicine. And Professor Lo, interestingly, enjoys, well, watching films, but more interestingly to me is playing video games, which I'm like, oh, I cannot imagine you playing video games. Really? What kind of video games do you like to play?
Actually, believe it or not, this week, of course, is Black Myth Wukong, so which I find actually to be exceptionally difficult to play. So you might see less of me for the next few weeks.
Okay, so that's, well, I think that's very, I was very inspired. I'm like, wow, Professor Lo playing video games and Professor Ho counting cards in Las Vegas.
It's very simple. The odds swing depending on the card count. And if it's favorable, you bet big. If it's not favorable, bet the minimum.
Okay.
Obvious to the math students here.
All right, so to kick off the panel discussion, one of the things that I found common between Professor Lo and Professor Ho is that they're both trained as medical doctors, right? But I'm more interested to understand, as a medical doctor, what shifted you from, seeing patients and practicing in the clinic to starting your own research lab, and what really drew you to a career in scientific research, and in particular, your research that you're most renowned for now? Professor Ho. Yeah, Ho.
I think being a curious person to begin with. As a youngster, I was curious about the world, why things are the way they are. And naturally, I was quite interested in sciences, and I began in the physical sciences. But gradually, as I learned more of the modern biology, I thought that was extremely interesting as well. And this is way back in the 1970s. And thought that the science was challenging, and at the same time, one could make an impact on the world in a very tangible way. And that's what shifted me from physical sciences to life science. And then during my medical training, at the very final year, fortuitously, I just bumped into a patient who presented to the hospital with a multitude of infections without a clear explanation. And it was obvious that his immune system was destroyed, but we don't know what. And from his medical history, it raised the possibility that it was a transmissible disease. And that turned out to be the very first case of AIDS. And in rapid succession, I saw 4 more cases in the ensuing months. And they had a common denominator, and that was they were all young homosexual men. And that was the beginning. And I, being the curious person, I wanted to know what was accounting for this, because any description of a similar syndrome was not found in the textbooks. And that's what drew me in. And while it was an esoteric disease at the time, I was curious, I wanted to know why, and I had the conviction that it must be important scientifically. And I've been committed to that mission ever since.
Thank you. And Professor Lo?
So I was a student at St. Joseph's College here in Kennedy Road. And I remember, actually, I used to go to the library to actually read scientific magazines, like Scientific American, Discovery. And then I'm very fascinated, but really by the stories of scientists. And then, of course, in Cambridge, we have actually many important discoveries over so many centuries. So after St. Joseph, I was accepted by Cambridge, and there I started to study medicine. And I remember actually when I was there, I actually read an article written by Professor Y.W. Khan. It's called On the Slope Boat from China. And he talked about his experience, how he became a medical student and then gradually moved on to the US and then started his work on prenatal diagnosis. So that actually somehow, really make a deep impression in me, and I want to follow his footsteps.
So both have not actually done any research in other areas of work. So prenatal testing and also HIV was something that you jumped right into for research.
For me, I was already quite interested in a number of infectious diseases by the time I was finishing training, and possibly many of the unexplained diseases could have infectious etiologies or infectious causes. And so I was leaning in that direction when the encounter with the early cases of AIDS occurred. So, and we had a strong suspicion that was a new infectious disease. So it was a perfect fit for me anyways.
Actually, I've worked in other areas before, because what happened is that in those days, Cambridge will only accept you for 3 years, preclinical. And then after that, one has to apply elsewhere. So actually, I went to Oxford. And there, actually, I went to a lecture given by somebody called Professor John Bell, who is now the Regius Professor of Medicine in Oxford. So he actually talked about a method, which at that time was new, called the polymerase chain reaction, PCR. And he said that this method is going to change the world. So after the meeting, after the lecture, I went up to him and asked him to teach me, which he did. And then I sort of, like a young kid with a new toy, so I would start playing with it. And initially, I tried to actually use it to detect viruses, like hepatitis B. And then, when I actually went to obstetrics lecture, I learned about pregnancy, learned about prenatal diagnosis. And then I thought, well, maybe it is sensitive enough to detect fetal cells in the mother's blood.
So you sort of combined the best of both worlds, and did your own research. So, of course, another common thing between you two are both are highly successful academics, but both have also translated your research findings, through either spinning off your own company or collaborating with industry. And everyone knows that, the road to commercialization or entrepreneurship it's always very challenging. Maybe can you share with us, some of the things that you've learned through this process, and if you had an opportunity, what would you have done differently?
Well, this might require a long answer, but I'll keep it as brief as possible. I think, doing science for the sake of science is already very gratifying to those who are curious in nature. But at the same time, if we're working on an important problem, we could make an impact that's positive for society, for humanity. It's gravy, right? So, so naturally, as we pursue our basic science, we wanted to translate that into meaningful solutions or interventions for the patients, and we don't formally train to do translational medicine, so it's learning by experience, and the one thing I've learned is that it's really running a marathon. You really have to think it through from beginning to end. A lot of people just jump in and say, "Oh, I have this basic science discovery, I'm going to apply it." But in addition to the basic science, you have to think through some of the engineering issues, manufacturing issues, clinical trials process, and finally the regulatory approval process. And it's not easy because it requires many different skill sets, and often it's not achieved by a single person or even a single team. It's through lots of collaborative efforts. And so I'm still learning, even though we have developed a number of products and therapeutic approaches, but just multitude of things to learn along the way to do it well. And each step is what those in the industry might call valley of death, because the chance of failure is exceedingly high. So it's not easy to make a product that is, in the end, given to patients.
I agree with David. I think it's really a continuous process of learning and also making mistakes. So one thing I learned very early on is the importance of intellectual properties, like patents. Now, for example, I remember that after I learned how to do PCR, one of the first experiments I did was to actually incorporate modified, nucleotides into it. And I find that it actually works, which actually is already patentable. But in that time, I didn't realize that. Because imagine, actually, that patent would be very valuable because you can produce probes even when the sequencing reaction are basically incorporation of modified nucleotides. So I actually remember that after I published that work, the people who invented PCR actually invited me to contribute a chapter to the first book on PCR. So I was, of course, very flattered and very happy as a medical student, managed to write something in the textbook. So after that, I've actually decided to learn more about the patenting process and to do that. And I still remember, actually, sometimes we make mistakes because when I first came back, which was in '97, and at that time in Hong Kong, academics were not encouraged to actually start our own companies. So I remember, actually, the very first patent that I had in this non-invasive prenatal testing space, our university actually made the mistakes of licensing it to a technology wholesaler. So in other words, that company is not interested in commercializing that test per se. They just collect IPs and then relicense it elsewhere. And now, looking back, it was actually foolish to do that because they're basically diluting our income, right? And then doing nothing. So after 3 years, they just thought that that patent was useless. They gave it back to university, which was lucky for me because the that patent subsequently was very, very valuable. Yeah. So basically learning and then trying to correct mistakes. Yeah. Thank you.
You talked about patents. Rumor has it, correct me if I'm wrong, that every staff and student in your lab has to learn how to write a patent. Is that true?
Yeah, that's true. So all the students, when they came in, I actually encouraged them to learn how to do it. Because if you don't, if you don't learn early, how do you protect, the invention? And also one thing very interesting about patent is that litigation is also very important. So now with lawsuits, it's almost like learning kung fu, right? But if you just learn to move without actually getting into actual fights, you'll never, you'll never be good. I know David is actually an accomplished karate player, right?
No.
Oh, really?
I wish I were.
I remember reading somewhere that you're actually into martial arts, is it?
Not true. Not true.
Rumor.
Ronnie could probably beat me up.
Following up on what Professor Low mentioned, it's when you said when you came back to Hong Kong, there was no incentive or no encouragement for academics, right, to do tech transfer. But of course, the landscape has really changed in recent years with the government injecting a lot of incentives, a lot of money, resources around the area, mainly ITC funding, right, which is for applied and translational research, which I think is also great. But can you comment a bit on this and also the balance between ITC funding and RGC funding, which is RGC, of course, more for basic research, and the balance between the both, and and what more can Hong Kong do better to boost our strength in this area? Yeah.
The level of funding is definitely much better than before. Now, when I first came back, say 28 years ago, at that time, RGC grant, you're talking about maybe 400,000 Hong Kong dollars. That's our grant. So Nancy will probably remember those days. And actually, that was my startup. Basically, my startup package was 400,000 Hong Kong dollars, and then you expect to, get on. And then I remember actually my very first RGC grant was actually rejected. It was actually the same thing which now is used clinically. And then after that, I see that with the introduction of ITF, we start having a grant which is several million Hong Kong dollars. And then with the Area of Excellence grants, theme-based research grant, we're talking about maybe 40, 50 million that's of money. And now with ASHK, we're talking about even several hundred million Hong Kong dollars, which is unimaginable previously. But of course, I think that the RGC grant, the basic science is still important, because if you don't have the basic discovery, there's nothing to commercialize. I mean, after all, for example, like fetal DNA maternal plasma is a basic scientific discovery. And from that we can do an invention, which is the testing.
Similar question to Professor Hope, I guess, in the landscape in the U.S. Do you feel that funding has changed over the years, and do you foresee more changes with the new presidential election coming up?
Now, the funding levels in the U.S. for medical science has been pretty steady, regardless of who's in the White House. In that, it's the Congress that appropriates the budget, and both sides of the aisle really do support medical research rather robustly. And so it hasn't faltered much. And for AIDS research, there was a period of rapid growth because of the expanding pandemic at the time. So we're pretty well funded, and we've gone through 4 years of Trump administration without too much cut to medical research. So it's somewhat reassuring, even if he makes a comeback. But we don't expect too much to change in the near future.
At the university in the U.S., how much does the university drive and incentivize the colleagues to, translate their research? Because I feel that in Hong Kong, it's a bit limited. Although the landscape has changed, but it's still, it's still not probably part of your key performance index when you do tenure and promotion. And when I talk to your junior colleagues, they say they feel that, this is something that, they probably don't want to focus on until they get their tenure and promotion. But how is that different maybe in the U.S.?
Well, I think if you're a scientist and you need your university to drive you, you're in trouble. I think the university, I think their role is to make sure the infrastructure is there to facilitate your work and the environment. So at top institutions where I've worked, the scientists don't need any more motivation except support, infrastructure support and monetary support. And many of the universities simply do not provide a lot of our research funding, because if we're doing well, we should be able to fund ourselves through the NIH and through other funding organizations. And that's generally been my rule. I think we tend to support ourselves.
So what I find is that for many professors, basically they are academic at heart. So translation is really a new thing to them. And some of my colleagues actually find that filing patents to take away time from their core interest, right? So currently, actually, I'm the patent committee chair at CHK. So what we want to do is basically to make the professors have a more sense of ownership of the patent. So what we do is that we actually encourage them, if they think and are confident on the technology, to actually fund the prosecution in return for a high share of the eventual income. And actually we find that for inventions that the professor themselves actually invest money, the probability of it actually being licensed out is actually higher, and the speed of licensing out is better. So I think we probably can really try to encourage them in this way.
I agree. I mean, all scientists have to be self-motivated. I think, like Professor Low said, it's really the comfort zone that we are in. We're trained as academics. We train our work in the lab, write grants, write our papers. But it's leaving that comfort zone to move out and to do the entrepreneurship part, which is not what we're trained, for. So that's an easy part. But I think it's very much needed, and sort of if the university can encourage that a little bit more, I think it will be helpful to for our colleagues. So moving on, I mean, what are the fun things about research? I feel is that we're always learning, right? We're always learning new things. There are always new technologies that are coming through. So can you share? Are there any new emerging research areas or scientific trends that particularly excite you? And which new technologies do you believe will have the most significant impact on your research? Please.
There's simply too many emerging areas that interest me, but I think if I have to give one answer within the life science area, it would have to be neuroscience. I think that's the new frontier. We seem to know so much about each of our organs except one, and that's the one on the top. And we still don't understand why we dream, why we sleep, what is consciousness, how our circuits are wired. There's just so much unknown. So if I were to start anew in life science, I probably would pursue that area. But there are so many areas in cancer therapy or cell therapy, stem cell research. The field is replete with many promising areas at this moment.
In your line of research, is there any new technologies that you have adopted to propel your research further?
Yeah, we're constantly learning. Single cell technologies, for example, has been fabulous for us. We're now, you used to take years and years to get a small number of monoclonal antibodies, for example, to target certain viruses. Now we could get hundreds, even thousands in the course of a few weeks, and then screen them for the most promising ones, and which is what we've done for SARS-CoV-2, the causative agent of COVID, which is what we're doing now for avian influenza, just to come up with countermeasures against these novel viruses. Now, and then antibodies, once we get them, we could solve the structure of those antibody bound to the antigen on the virus rather easily within a few days' time by cryo-electron microscopy. We could solve those structures in a matter of days. It's just amazing thinking back and comparing what we could do now to even a decade ago or 2 decades ago.
It's fascinating how we can sort of answer this, try to look at the same question but at a completely different angle with new technologies nowadays. Professor Low, yours?
Actually, the first area, I agree completely with David. I think neuroscience is really incredible. And also, as a medic, I would say that some of the diseases in neuroscience where really modern society as it is not really geared up to face, like Alzheimer's disease that Professor Nancy Yip has contributed so much. Because I'm sure that all of us actually know somebody whose life is actually changed with Alzheimer's. And I think if you're talking about disease in which 1/3 or 1/4 of people over the age of 85 will have it, so how can we cope? When we're boasting that Hong Kong has one of the longest lifespan, in the world, we really have to find new cures. Now, another area I think is aging. What is the mechanism of aging? For example, there's all sorts of molecular clock talking about difference in chronological age and biological age, and can we measure the different aging of different organs? So I think this a fascinating area. And the third area, of course, is AI. We're now combining, say, in my own area, genomics with AI, and then find that you can discern patterns which you cannot before. Like you just give us a sequencing trace, and they can find epigenetics alterations, and yeah, I think this is a really very exciting future. Yeah.
Related to that, can you share with us some of the new research areas that you're currently working on?
Well, I have worked on HIV/AIDS for 43 years, and at the beginning of 2020, a new pandemic struck, and we paused that research, paused the AIDS research to almost entirely focus on COVID. And there was a very steep learning curve, but the skill set we had from one area of virus research was applied very rapidly to another. And so that was a great transition for us. And I believe it turned out to be one of our most productive research period. But now that the COVID pandemic is largely over, although infections are still occurring, we are thinking of what will come next. And my expectation is there will be more pandemics because of climate change, because of population growth, because of transportation, and the fact that human beings are invading the territory of other animal species. We're going to have more and more zoonoses or cross-species transmission. And so we're thinking about how to properly prepare for the next pandemic. And hopefully we do better than what we did in 2020. There is that one pathogen that's knocking on our door, and that's avian influenza that actually first struck Hong Kong in 1997, killing a third of the cases infected. And this one now is widespread in the Americas, infecting not only birds, but many, many different mammals. And so we're very concerned about that. But of course, no one knows what the next pandemic pathogen is. So we have to really gear up in a very broad way to see if we could now develop countermeasures that are very broad. One example is to utilize our innate immune responses. That everybody knows about T cells, B cells, and antibodies, but we actually have a frontline defense, which we call the innate responses, that could recognize patterns on pathogens and react not in days or weeks, but within minutes to hours. And I think we could exploit our innate immune system to counter future threats in that way.
Marcelo?
I'm working on the fragmentation of DNA. So you can imagine when you look at a cell, the DNA are very long stretches of molecules like a chromosome. But when you look at DNA in blood, because it's some sort of cell death byproduct, the DNA is fragmented in bits. And for many years, people assume that fragmentation is random. It's almost like you try to shred your paper by a shredder. And of course, you think that all these strands which come out are random. But we and others have shown that actually it's not random at all. And actually from the way it's fragmented, we can actually tell what disease the person has, like cancer or other disorders.
And you're using that to detect NPC and many different cancers.
We're actually using that to detect different types of cancer. And actually interesting, the way I actually arrived at that was actually through looking at a painting.
Really?
Because actually once I engage a painter to draw something, which is very simple, just a railway track, and then with some signal lights, and then the gates coming up and down. And then when I look at that, I thought, well, maybe the signal is cancer signal, methylation signal. And the gates, when it come down, would it chop the railway, which looks like DNA to me. So by looking at how the railway is chopped, we can actually decide what that signal is. So that's why I call that technology fragma. So
Inspiring. You never know what goes through a scientist's mind, I tell you. Very inspiring. Did you have something to add on? Or
No, no.
no.
I don't look at as many paintings.
actually, if you're interested, this painting is going to be exhibited in the Hong Kong Science Museum from the 4th of October onwards for 1 month.
Okay, well, we'll take note. We have to go visit Science Museum.
But I will add a note about, you mentioned earlier, and Ronnie did as well, sort of having championed the antiretroviral, combination antiretroviral therapy. The basis for that actually came from mathematics. And it's not, I went to college at Caltech, and we're required to take 2 years of math beyond calculus, required. And so math, even though I don't do it anymore, seemed comfortable to me, whereas math often is not comfortable to life science, scientists in the life science area. So we actually worked on trying to understand HIV dynamics. So trying to quantify HIV, and it turns out that there's a steady state that's maintained for HIV for a long, long period of time. And during a steady state, every student knows here, virus production equals virus clearance. But you don't know whether that number is very high or very low, and turns out to be enormously high. And that is figured out by nothing more than high school calculus. By generating clinical data, fitting it into two sets of equations that any one of you could write, and then come the answer. And from that, you could discern the mutation rate of the virus, and from that, you come to the conclusion that if you treat this virus with one drug at a time, you're going to inevitably fail. But if you start to force the virus to make a combination of mutations at specific positions, it becomes increasingly improbable. And that, when one realizes that, you rush to the clinic to launch the combination trial, which we did over the course of a year, 3 different trials, all yielding the same result. And that's the beginning of the combination therapy.
Mathematics, very important.
It's the language of science.
That's right. So we got a lot of students here today, right? Do you have any words of advice to them for those that are passionate for pursuing a scientific career? I'm sure they're all here for a reason.
Well, again, this might require a long answer. I'll give the same
We have time.
answers to the ones that I give to my graduate students and PhD students. I think it applies generally. I think, you got to pursue something that you're passionate about. If you're not interested in the topic, you're not going to be dedicated. So the word passion is very important. I think the other is a willingness to take some risk. And I'm not talking about wild, crazy risk. I'm talking about informed risk. And, as been said, unwillingness to take informed risk is acceptance of mediocrity. And so you at certain times you have to be willing to take the risk. I think for me, I took the risk to jump into an esoteric disease that turned out to be a huge pandemic. There were many people advising me not to do that, and I made the right bet in that circumstance. The other is, I think everybody knows, you have to be strategic. But by that, what does one mean? I have lots of graduate students and postdocs, and they do experiments, and they get results, and they think of 20 different things to do, right? But what are the things that they should be doing? So the word could and should come into play. In the English language, they're often used interchangeably, but incorrectly. In Chinese, 可以做,应该做 is clearly very different. And so I tell my postdocs in particular, you got to focus on the ones that are in the critical path of your project. You could do a lot of things, but if, I asked them, if so what? If the answer is not consequential, why do it? So one has to be strategic in that sense. And then it is also important, particularly in science, to discern the difference between truth and dogma. We have a lot of dogma pretending to be truth, even in the scientific community, right? Sometimes certain theories are talked about so much that they become standard dogma. And particularly in the Chinese culture, whatever the senior professor says becomes gospel. and that's not necessarily the truth. So I ask the younger students to always think about challenging the superiors with questions. And I think these things are very important, but the most important thing is to stay curious and ask a lot of questions, and if you're curious, you'll never stop learning.
Thank you. And Professor Lo?
I think by being a scientist, one is offered a very precious chance to be the first one in history to see something, to discover something, and that really is make everything is worth it, all the difficulty. And then if for those students who are interested to become a doctor, then being a clinician scientist will actually give you a very interesting opportunity, because as a doctor, even if I work very hard, I can perhaps see several dozen patients in a day. But now, if you're a medical scientist, you can actually might discover or invent something which can benefit millions of people every year. So I think that alone, I think, make it worthwhile.
It's fun. Yeah. So I'm mindful of the time. I've been reminded that I should move into the Q&A session. So questions are now invited. I see a head shooting right about at the back, and a microphone is coming your way. Yes.
Hi, Professor David and Dennis. My name is Gigi. I'm a mother of 3. So I benefit from your research, Professor Dennis. So thank you so much. My 2 kids are outside. I'm sorry they may be screaming a little bit because I'm still in my postpartum. But I think I need to come here. I did my PhD in Singapore and Israel on biotech and stem cells, and then returned to Hong Kong. And for the past 10 years, I've been working on R&D commercialization. I encountered 3 major problems from my 10 years, and I really want to get your advice. First of all is when we talk to professor, because I work with a lot of spin-off, and professors are the owner of the inventor. They are a little stubborn. When it comes to, because we need to bring the science to business, right? So there's a balance between business and science, and sometimes they are really stubborn about standing firm in the science. But you know that if they stand so firm on that, it cannot move forward. You know, the investor will not happy. It will be a long go-to-market. So how should I talk to them? My second difficulty is about regulatory that you mentioned, because Hong Kong regulation is always so behind. So some of the new innovation talking about stem cells, like what are the regulation now? So some of the very nice R&D outcomes, they cannot be really applied because of the regulation. So they go to Taiwan, they go to Thailand, but not Hong Kong. How can we do that? My third question will be, sorry about that, my third question will be about really the funding issue, because you mentioned we have ample funding, but with a lot of clients that I work with, their funding, most of the funding spent on their offices in Science Park. The human resources may be junior technicians, but not really on their R&D, and not really on smart IP strategy. So how could what can I do more to support Hong Kong R&D commercialization? Thank you so much.
I think that's for you.
Okay, thank you. Thank you. Now, so I think that, for example, I work with my VC in the long term. You know, I've know those partners for, let's say, over 10 years. So I think you probably really need to develop a trusting relationship with the scientists, so they can understand. I think it's really talking about walking on a rope, which also at the same time we uphold the highest scientific standards, and at the other time to make sure that it is practical. Now, just now I mentioned about having the scientists have a sense of ownership on their IPs to even invest in it. And I find that actually when the professors start investing in their own IP, then suddenly the perspective is different, because they believe it's their stuff, right? It's almost like your home. Instead of just giving it to a decorator who to decorate anything that he or she wants. But now the scientist actually start to design something himself or herself. So that would be different, right? Now, in terms of regulatory, I do agree. In Hong Kong, actually, the authorities tend to be very conservative. Now, for example, like when we launched NIPT, I did the trial in 2011. Actually, I find that in the UK and US, they start doing it in 2014. But in Hong Kong, actually only managed to persuade the authority to do it in late 2019. Yeah. So, but I hope that with the large investment into technology now, I think the Hong Kong government for the last 5 years has invested something like 200 billion Hong Kong dollars. So I hope that with that sort of investment, they will think that, well, just the money is not enough. They also need to have the regulatory part to actually let the investment come to fruition. Yeah, thank you.
This gentleman.
Hi, I'm here with my partner, Jennifer. My name's Gabriel. We work in AI and trust technologies, and we were wondering why and why not use AI in your field of research, and how would you apply it, and how would you not want to apply it? Thank you.
You're asking this?
Both of you.
Okay, David.
Well, we actually do use some AI to help with structural predictions when we don't have the actual physical structure. So we do. And also, as Dennis mentioned earlier, when we have lots of sequence data that human brains are not capable of resolving, we do apply neural networks to help tease out certain details, but we don't, we don't use it as the main tool, but we as one tool in the toolkit. I don't want to keep going.
So similar to David, I also use AI machine learning in my research. But that said, I think that it is important to have a mentality not to be quote unquote lazy, because some scientists, especially some of say students who are just starting off, they will say that, well, you have this of a machine learning model which seems to give you a very good prediction, right? And then they just thought that is the be all and all. But I actually think that is much more satisfactory if you actually know the actual mechanism, the actual basic science surrounding that. And whatever prediction you get from understanding that mechanism will be more robust than the AI, because you never know. The AI may overtrain, it may have some batch effect and all this stuff. Thank you.
Hi, I'm Jennifer, and I'm Gabriel's friend and colleagues. I'm the council member of International Data Science Olympia, and I'm also a startup founder in Science Park. And I am a person that with a machine learning background, so I don't really have medical background like you guys. So for me, I am very interested in like medical field, the research field in medical science as well. So I want to know, like, when you're applying AI technologies on this field, what are the limitations or like concerns that you face or challenged by your investor or like people that's going to use your products? So I want to hear like the opinions and views on both of you. Thank you.
Well, in my area, I think AI applied selectively has been wonderful. As I mentioned, in helping with sorting out sequences and structure. But we also see a lot of overly ambitious applications that go nowhere. And I'll just give you one example. We want to know where SARS-CoV-2 is going. How is it evolving? We've been monitoring it ever since 2020, and it's evolving extensively, right? The virus today is very different from the virus 4 years ago. But where's it going? But the changes have been gradual drifts, but major shifts. And these occur through what one might consider black swan events. And how are you going to predict that? And so consequently, there are lots of AI papers out there in the scientific literature. But to me, most of them are pretty crappy and have no reflection of reality. So I think one doesn't want to overpromise with AI. But I think AI is going to obviously be very powerful if applied wisely. But then, all these false promises are not good for the field.
I think that what makes a company valuable is that it has to have protectable IPs, protectable technologies. So the question, of course, with AI machine learning is that the patent protection could be difficult, right? Because some people might argue, is that algorithm, or are you just basically just shielding your data set from others? That's your core value, rather than actual, patent. For example, in some of the other area like drugs, right? Composition of matter is a very powerful type of patents, So I think this is an area that you need to think about. And also just now I mentioned about overtraining, batch effect, that sort of thing. Because sometimes, like in my field, when you do sequencing, if you change one reagent, it's possible that that will completely confuse your AI, your trained algorithms. Yeah.
Other questions? Yes, this lady at the front.
Okay, my name is Vivian Nam, and I'm a mathematics teacher, and I'm very glad to hear your sharing. And I have two questions. For the first question is about the patent. So when Professor Low encouraged the patent protection, but I just wonder if the patent protection will affect the sharing of knowledge or the chances to expand the knowledge. And also, it may affect poor people to use it. And for my second question is about the recent political environment in Hong Kong. So to my knowledge, some of my friends from the US, when they come to Hong Kong, they said they cannot bring their computers to Hong Kong because the US may affect the spread of some precious knowledge to China or to Hong Kong. So I wonder if that will that also the same too. I wonder if that is also the same in medicine field, and I just wonder if that will affect the research development in Hong Kong. Thank you.
So maybe I'll attempt first. Now, so actually, I think that the patents issue, I think we're really trying to have a system which is a compromise between what benefit we give an individual or company to what benefit we give to the society. Now, because you can imagine, if you don't have patents, it's difficult to persuade investor to spend hundreds of millions of dollars to back a technology or to back a drugs, okay? But on the other hand, if you don't have patents also, then you probably, the alternative is trade secret. It's almost like in the old days, you read some Chinese novels about some secret concoction or secret kung fu, that sort of stuff, right? So if you have this sort of secret, 家傳秘方, right, then science probably won't develop either. So I think with patents, basically what we're saying is I give you 20 years of quote-unquote monopoly. In exchange of that, you have to tell me your secret. And you find that actually 20 years is actually very short. For example, like in my area, it took me 11 years to bring the test to the clinic. And so we're just, in a way, benefiting a few years. And for drugs, it could be just 5 years. It could take you 15 years to bring it to the clinic. So I think that currently that system is okay. And also another thing is that sometimes we have to be not too thinking, even if I don't have a patent, do you believe a company, when they use this technology, do you think that they're going to give it free to people? They're not, right? But whereas if I have a patent, if I receive some income, I could decide that I wish to donate to Asian Society or whatever, right? Charity I want, or Culture Foundation, right? So you can still do good. Yeah, thank you.
Let me just add one point regarding your first question. I think one way to do it is similar to, say, the philosophy of the Bill and Melinda Gates Foundation, and that is, yes, you go ahead and you patent, and you go ahead and make your profit in the wealthier nations, but you sign a global access agreement so that in regions where these drugs are not affordable, they could have access. And that's a pretty decent compromise, at least in areas where I work. Regarding your second question, I did bring my computer, I did bring my iPhone, but I don't work for the US government. And many US government officials now have to come with an empty computer and an empty iPhone because of security concerns. And I think it's a bit excessive, but
Yeah, maybe I'll also add on the second point. I think that unfortunately, because of the current geopolitical environment, some of the policy or developments could actually adversely affect scientific progress. Now, for example, I read there's a directive from the White House about the bulk data, biological data, being not exportable to certain, countries, etc. So of course, I'm worried that that might affect data sharing. What is bulk? I mean, is that 10 cases, 50, 100, or 1,000? That might make initiative like biobanks, untenable.
yeah, it's a two-way street, right? Because China will not let any samples go out, right? And if weren't for Australian scientists, the sequence on SARS-CoV-2 would not have been released as early and probably would have slowed down the development of vaccine and antibodies. So I think both sides need to think about the geopolitics here. I mean, there's a great deal of misunderstanding. And I see it on the US side. There's a total false narrative going on about what's going on in China. So it's a huge problem that we scientists cannot fix.
Any other questions? Well, okay.
Sorry.
Microphone is coming your way. Yeah.
Hi. Good evening. My name is Adrian Chan, and I'm a high school student at Phillips Exeter Academy in the US. My question is, how might you use CRISPR and its related Cas proteins in your research, such as improving monoclonal antibodies or the complement system in Professor Ho's research, or potentially tagging DNA fragments with a his tag, or knocking out certain genes in Professor Lo's research?
Well, in terms of using CRISPR to tackle antibodies, I think we have other methods which could be more easily applied. In terms of using CRISPR to address HIV, we have very good therapy. Patients could live a pretty normal lifespan, but we don't have a cure. And the question is, could we use CRISPR technology to cut the virus out of the integrated genome? Or could we use the CRISPR base editing technology to render the virus non-infectious and go for a cure? In theory, that sounds pretty good, but in practice, in terms of delivery and efficiency, there are lots of challenges still. So I don't foresee a positive outcome anytime soon, but it is being pursued by many groups and including by some of our scientists.
So I work in a diagnostic area. Now, so human genome, we consist of 3 billion base pair, so code. And traditionally, if I want to be a cost-effective test, I have to just target a bit of that 3 billion, right? Typically using techniques like PCR to amplify that. But the problem is that PCR copies DNA, but when it copies, some information is gone, like the epigenetic information, which is like formatting of the DNA. So what we can do is you use CRISPR basically to say, okay, just cut that bit, and so that I can analyze that bit. So that's how my group is using it.
So, I mean, there's a lot of burning questions, but maybe we'll see if the panelists have time to take them at the end. But I've been reminded to bring this to a close. But what I want to do is actually end by just asking 2 more quick questions. And so to Professor Ho, if you were not to be trained as in medicine or become a scientist, what profession do you think you would have captivated your interest?
Oh, I dream of being an NBA basketball player. if I were a foot taller.
And you played basketball. You said you played basketball.
No, but a more serious answer might be being a mathematician, actually. I didn't say that just for Hang Long. I was always interested in math, and when I was in ninth grade, I think the geometry teacher said, if you could solve this problem within a week, you get an A. And I solved it. So I always enjoy math, and the math helped me with life science research.
And Professor Low, if you were to be a student again, if you were going to go back to university, what is that one subject that you wish you had taken?
Actually, just now, David talked about importance of mathematics. Unfortunately, I'm one of those biologists who did biology because my math is so bad. so I think that if I go back to school again, definitely I want to, brush up my mathematics more.
Do it better. Do it
Yes.
better. Okay. All right. Thank you. So, this brings us to a close. I hope that you find it very inspiring. I certainly did, and please join me in thanking the two outstanding panelists again. Thank you.
Thank you, Stephanie.
No, thank you very much.
I'm just an announcer of, let's take a group photograph, everybody. Is that okay? We will have 3 chairs out here so that the 3 of you can sit down there. And then the photographer will come from on top. Yeah. Well, ladies and gentlemen, I think the difference between an hour ago when I stood up here and now is that every one of you, ladies and gentlemen, are a little bit smarter than before. Keep tab of the programs that we are still presenting for the rest of the year, so make sure that you come. I think it is really worth your while to spend an hour and a half here and learn a lot. The last program on AI was really very eye-opening, and it's also very good for people who really want to have a general knowledge of a subject from some experts, and yet you don't usually devote the time to do so. And I think the same thing with today. I think that we have learned quite a bit. It is said, and anyway, I better not say too much. Ladies and gentlemen, can we also have all the students rise and to be recognized? 好嘛，請啲學生企起身啦，好嘛？ I think finally we should have another round of applause for our moderator, Professor Stephanie Ma, our 2 speakers, Dr. Dennis Low and Professor David Ho. See you next time. For those of you who have signed up for the A Society dinner tonight, upstairs we'll have cocktail first and then followed by dinner. See you there.